Okay, just trying to explain RSA encryption. Hopefully this is good enough. Otherwise, we'll figure out another way to explain. So RSA encryption, it comes from the name of the inventor, Rifus, Shamir, and Edelman. So based on their theory, and it's using mathematical properties and using very significantly large numbers. So to find a large prime numbers is quite difficult, and it requires a lot of computing power as well. From the two large numbers, we will generate a public key and a private key. So public key is something that you can freely distribute inside the operating system or you can distribute to everyone. But the private key is normally what you store in the server. So for example, in your web browsing, so the public key is something that you can send to everyone to use. So when they go to the website, they will use the public key to encrypt the request, but the server will hold the private key to unlock to decrypt the request. So how that works is quite simple. So so the message then gets through the public key, and that becomes encrypted, and then it gets sent through the web. And then when you receive it, you run it with the private key, and then you will actually get the actual message. So why is it secure? Is that, as I said, because of the factoring. So factoring large numbers, it takes a lot of computing power, especially when you're talking about the 2048-bit key, so very significant large numbers. So it's currently using in the secure web browsing, your digital signature, how to lock your email, and also TLS or SSH, basically the text message connection to remote computer. So that is the simplest way of explanation of RSA. So the next slide will be how you generate the RSA. So these are the steps to generate the key. And then once you come up with your, where is the mouse gone? Once you come up with your public key and your private key, then you can use it to generate. So you're using this modulus. So you can see here we've been talking about modulus. So that's what it's doing. So I have got an example in the small numbers to help you. So let's just say we just pick the, no, the small numbers of p and 5 and 11, and then we just have to multiply them. So we gotta have to calculate n. So p times q, 5 times 11, 55. So these 5 and 11 are prime numbers. So we got 55 as the first number that we need. Then we have to compute this one here. They call it Euler's Tothian function. It's basically reduce the p and q by 1 and multiply. And then we have 40. We're not going to use 40. 40 we're going to use on the next calculation. So the next calculation is that we need to find an E. So an E is basically a prime number that is sharing only one factor that is the same as 40. So don't worry about this formula. I don't even get it as well. But the whole idea is that we normally choose either number 3, number 17, or number 65537. So now we have 55, we got 3, and then using that one, we now need to find a D. So D times 3 needs to be equals to 1 modulus 40, which technically this one here will end up 1 modulus 40 will always end up as 1. So this is where you do a guessing game and you try to find the closest number. So in here we come up with 27 because 27 times 3 is 81 and 81 modulus 40 is 1. So now we end up with this private key and public key. So if we're going to encrypt the process, we need to convert the letter into a number. So let's say we encrypting letter M. So what we want to do here is that we need to do, you got E and N here. So this is the formula. for encryption. So 9 to the power of 3 modulus 55. So you got 7 to 9 modulus 55. So then you're going to end up with 14. Now, you won't be able to reverse back the formula because 7 to 9 modulus 55 is 14, but 14 modulus 55 is also 14 as well. So that's why you cannot decrypt the number using the same key. So with the decryption process, as you can see, we actually have a different number here. 55 is the same, but the D is different. So now we're looking at 14. So now what we need to do is that the formula is similar. So basically 14, but this time here we are pulling it up to power of 27. So as you can see, the number starting to grow as well. And then we do modulus 55. So that's our normal computer. Long integer can only handle like 2 trillion number. So to handle this number, there's gonna be some sort of efficiently computing powers to run it. But just if you want to try it, you can try to divide it. But just trust me that this modulus 55 will end up with the letter number 9. And then that number 9 is then you convert it back into alphabets. So that is how it works. So you don't actually need to know the theory on how we generate the key, but this is how to give you an idea how they have a methodology that allows you to use two separate keys to encrypt and decrypt messages. So that is the very simple one. So the whole idea with this one and why it's secure is that the public key allows you to this allows you to distribute this with any of your software or any of your web application without the need to worry about um, security compromise. So that is the reason why this RSA is secure. Hopefully that helps. Thank you.